Hi everybody, we continue review in Calculus 1. First, we have critical points. Critical points are the points where the derivative equal to 0 or does not exist. And it has to be in the domain of the function. Right, so let's start. So of course, first thing we do is find the derivative. So we take derivative, and that will be 3x squared minus 18x. And we just have it equal to 0. Or does not exist. Equal to 0, 3x squared minus 18x equal to 0. We can factor out 3x. And we have x minus 6 equal to 0. So 3x is 0 or x minus 6 equal to 0. 3x equal to 0. So x equal to 0 and x equal to 6. The derivative is a polynomial, so this is defined everywhere. So here we don't have anything where it does not exist. Right, so we found the point x equal to 0 and x equal to 6. Last thing we need is make sure it is in the domain. So we're going to check with the original function. And check this is the function. So we're going to put in 0 for x, and then we're going to put 6 in for x. Just use the calculator quickly. Right. So I hit y equal to, I enter the function x cubed minus 9x squared plus 4. And we hit second and trace the values. So hit enter again. We'll graph the function, and then we'll ask you what is x equal to. We say x equal to 0, and give us the y values is 4. And we hit 6 for x equal to 6, y equal to negative 104. And both of these are defined. Meaning the points belong to the domain. So we have critical point x equal to 0 and x equal to 6. Sorry. Yeah. So that is the first one. Now we go to the second one. This is a little bit longer, so try to write very small. So the same thing. First we do is we take derivative, and then we make it equal to 0, does not exist. And then we will check in the domain to make sure that the function is defined at the point. Right, so we'll take derivative. 128 square root of x, let's rewrite that as 128 x to the 1/2. And we'll take derivative of that power rule, take the 2 down, that ax minus 128 take the 1/2 down, and then x to the negative 1/2, because original power 1/2 minus 1 is minus 1/2, and that's what we have, 128. So that gives us 64 ax 128, so that's 64 x to the negative 1/2. Let's rewrite this as ax minus 64. We have x to the negative 1/2 power, so move to the bottom, becomes positive. Right, so this we have a denominator, so we need to combine the whole thing into one big fraction. So what I do is I'll multiply x to the 1/2 top and bottom to have the common denominator. I'm going to do that on the next line. So x to the 1/2, x to the 1/2 minus 64 x to the 1/2. So common denominator is x to the 1/2, and the top we have x to the first times x to the 1/2. 1 plus 1/2 is 3/2, so ax to the 3/2 minus 64, and that is the derivative. Right, we do the same thing, equal to 0 does not exist. So the derivative equal to 0, or the derivative does not exist. Derivative equal to 0 is where if we have fraction that equivalent to the top equal to 0, and derivative does not exist equivalent to where we have the denominator equal to 0. Right, so we have ax to the 3/2 minus 64 equal to 0. That's the top. Move the 64 over and divide by 8. We have x to the 3/2. 64 divided by 8 is 8. Now, x to the 3/2, we can write this as square root of x cubed equal to 8. Right? Now to get rid of the square root, we will square both sides. This we don't have to check the answer because the square root has to be positive. So that gives us x cubed equal to a squared is 64. And finally, to get back to x, we take the cube root of 64. So unlike the square root, if this is the square root, we need a plus or minus. This is an odd root, so we don't do anything. We just leave it as is. Cube root of 64 is 4. You have x equal to 4. That's where the top equal to 0. The bottom equal to 0. X to the 1/2 equal to 0. Square both sides. X equal to 0. So we have those points, x equal to 4 and x equal to 0. And then we check with the original function. Original function y equal to 4x squared minus 120. Y equal to 4 times 4 squared minus 128 square root of 4. 4 squared 64. Square root of 4 is 2 times 128 is 256. It's defined. That's all we worry about. So that's good. At x equal to 0, y equal to 4 times 0 squared minus 128 square root of 0. and of course that is just 0. So both of them are defined, and so those are the critical points. Uh, 0 and 4. We go to the next one. This one we try to find the maximum or the minimum. So first thing, so that is a function. We find the maximum or minimum. Let's look at the problem. We have the function and we have the boundary. I mean the domain of the problem from -2 to 5. And this is closed. If it is closed and the function is continuous on that closed interval, we guarantee to have a maximum or the minimum. In this case, we only ask to find the minimum. Right. So first thing we still do exactly like this, find the critical points. So we take the derivative. The derivative of this is take out the 3. 3 times 1/3 is just 1, so we have x squared minus 4x and plus 3. So that is the derivative. And then we make it equal to 0, does not exist. Equal to 0, that equal to 0. We can factor as x minus 1 and x minus 3, because when we multiply it out, that's what we have. So we have x minus 1 is 0, or x minus 3 is 0. A product is 0 where at least one factor equal to 0. So we solve for x equal to 1 and x equal to 3. And both of those points belong in this domain. Derivative does not exist, we have none, because the function is continuous everywhere. I mean the derivative. That one is a polynomial, so continuous everywhere. Right. At this point, if we ask to find critical point, we should check, make sure that the function are defined at those points. But since this will find the maximum or minimum, absolute max and absolute min, so that's the key point here. We're going to put everything in the table, then we'll just test them. So we're going to test them anyway, so we don't have to check now. So next step, we go to the table. We're going to check it anyway. So x, we start from -2 and 5, and between there we have 1 and 3. The function 1 over 3x cubed minus 2x squared plus 3x minus 4. Right. So let's put on the calculator. Actually, I think I put there, we still be able to see it. Right. I will enter a function 1 over 3x cubed minus 2x squared plus 3x minus 4. Right. And then hit second trace when x equal to -2 values. X equal to -2. It doesn't give us fraction. Let's see if we can keep that as a fraction. If it doesn't work, we have to try something else. Okay, -2. Okay, -62/3. 1. -8/3. 3. -4. And 5 is A/3. So we don't have to check because we will check it anyway. So we're looking for the absolute minimum. So that is, this one is the smallest one. So we say absolute minimum equal to -62/3 at x equal to -2. Right. So once again, find the point where derivative equal to 0 or does not exist, and then we just test them. The biggest one is the max, the smallest one is the mean. Then we'll go to the next one. This will do the same thing. Derivative equal to 0 does not exist, and then put everything in the table, including the boundary. Right. So that we'll take derivative. X to the 2/3, we can bring the 2/3 down, so we have 5 2/3 x. 2/3 minus 1 is -1/3. And this, we have 10/3 x to the -1/3. Or negative exponent, we move it to the bottom. 10/3 x to 1/3. Right. And then derivative equal to 0. Derivative does not exist. We have a fraction here, so derivative equal to 0, meaning the top is equal to 0. Derivative does not exist, meaning the bottom is equal to 0. So what we have is 10 equal to 0. Obviously that doesn't give us anything, so there's nothing on this side. The bottom equal to 0. 3x to the 1/3 equal to 0. Divide by 3 on both sides. X 1/3 equal to 0. So x equal to 0 when we cube both sides. Right. Once again, usually we're going to check to make sure that this point belongs to the domain of the problem. Actually 0 is between -27 and 1, so that's one's good. Yeah. So the previous one we need to check to make sure that the point here belongs to the domain. But as far as checking the values of it, we don't really need to. Just make sure the numbers belong to the interval. This one it does. Actually, now we're going to put in the table of the original function. We have the function, original function, that is 5x to the 2/3. Now we have gone from -27 to 1, and the point in between we need to evaluate at 0. So enter the function 5x to the 2/3, and then we want to evaluate second trace value negative 27. Of course, it doesn't give us that because negative 27 is not in that window. That's alright. Just a second more to quick. Hit variables. Go to the function y variables. Function y1. In that case, we can do this easily. Evaluate the function at negative 27. We have 45. Put in 0, obviously we have 0. And put in 1, we have 5. Well, let's just do that again to make sure we have it. Should put the calculator bigger. There. Variables, y variables, function y1 at x equal to say 1. Right. So just like that. And so we have absolute max here, and absolute mean, sorry, is here. So we say absolute max equal to 45 at x equal to negative 27. Absolute mean equal to 0 when x equal to 0. Right. So that is derivative equal to 0 does not exist, and then put everything in the table. Make sure those points those points belong to the domain before we evaluate in the table. Right. Next, we'll find the interval, open interval, where the function is decreasing. Let me write the timestamp. So the routine kind of similar to what we did. Derivative equal to 0 does not exist, we find the point. However, this is asking to find an interval, not a point. So we don't really need to check to see what happened at the point. So we don't need to check. We don't need to check the points. To check for the critical points, we just need an interval in between. Right. But overall, it's still the same thing. Taking derivative of this, I will use the quotient rule. U equal to 1. U prime 0, v equal to x squared plus 1, v prime 2x. Derivative as quotient rule, u prime v minus u v prime over v squared, u prime v minus u v prime over v x squared plus 1 square. Right. 0 times anything is 0, so we just have negative 2x over x squared plus 1 square. Sorry. Next, we find the point where derivative equal to 0, derivative does not exist. So this will be kind of routine now. Derivative equal to 0, or derivative does not exist. equal to 0, meaning the top is 0. I just put 2 dots. Top equal to 0. So the count. Bottom equal to 0. So negative 2x equal to 0. We have x equal to 0. The bottom, x squared plus 1 equal to 0. But square equal to 0, so it will be equal to 0 without the square. Move the 1 over, x squared equal to negative 1. And to get back to x, we take the square root on both sides. Remember, when we do that, don't forget that's plus or minus. So we have x equal to plus or minus square root of negative 1. Negative inside the square root. So this one is undefined or imaginary. So it's not real. So it's just imaginary. Doesn't count. Right. At this point, usually we'll check to make sure that those points, when we put in the function, it is defined. But since we're asking for the interval, we don't need to check those points. Next, the different things here, instead of doing the table with the original function, what we do next is a sign chart. So we will have that is a number line from negative infinity to infinity. The point that divide the number line called partition numbers. We have x equal to 0 and there's nothing here. I should write none. On this side, so we have x equal to 0 and the derivative that is negative 2x over x squared plus 1 squared. Right. 0 is where the derivative equal to 0. So equal to 0 when the top is 0. And that number divide the number line. So we have the table divide x0. Next we're going to pick a point here and here. Those are the test points. I use negative 1 and 1. Put it in the derivative. Let's use a calculator again, even though it's fairly easy to do without it. Right. Y equal to, I enter the derivative, will be 1. This is, remember, the derivative, so will be negative 2x divided by x squared plus 1, and we square. Right, second trace and evaluate at negative 1 and 1. Negative 1 right, won't take too long. Right, there's something wrong with the calculator. So if you put negative 1 in here, remember the bottom is the square, or square is always positive. So the bottom doesn't matter what we put in it, it's going to be positive. If you put negative 1 on the top, negative 2 times negative 1 is positive. So this is going to be positive. And if we put 1 in here, that will be negative on the top. The bottom is always positive. Negative divided by positive is negative. So they're asking positive is increasing, negative is decreasing. Since the question asking for where the function is increasing, we say it is decreasing when x equal to 0 to infinity. Again, we leave an interval so we don't have to check the point. So that is 55. The same thing, find the interval where the function is increasing. So do this quickly. We take derivative for x cubed minus 36x, right, equal to 0. Does not exist. This is a polynomial, so it is defined everywhere. So we don't have anything here. We just solve this equation for x cubed minus 36x equal to 0. We can factor out for x. So we will have x squared minus 9 equal to 0. So we have for x equal to 0, or x squared minus 9 equal to 0. Move the 9 over. But first, for x equal to 0, so x equal to 0. Move the 9 over. X squared equal to 9, so x equal to plus or minus square root of 9. So x is equal to plus or minus 3. Right. Once again, this one asking for the interval, so we don't have to check the points. So we don't need to check the point. We just need to check the answer. We just want the interval in between, so we don't really need to check the points. Right. Next, the sign chart. Right, the number 9. The point we have is 0, negative 3, and 3. Just put them in the right order of negative 3, 0, and then 3. And the derivative for x cubed minus 36x. That is the derivative. Derivative equal to 0 at those points though. So we can just do that. Right. Now test point, we're going to choose the point in between. So negative 4, negative 2, 1, or 4. Right. Let y equal to, I'll enter the function x to the 4 minus 18x squared plus 81, right? And usually we just hit second trace and we enter the values. That's just fine. But since all those points are integers, If we hit second graph, we just have the table and we just look for it. X equal to -4, it is positive 49, sorry. X equal to -2 is sorry, I should enter the derivative, not the function. Right, do that again. For x cubed minus 36x, remember we use the derivative, not a function. Right, second table. Right, -4, it is -12. -2, 40, so it's positive. At 1 is negative, and at 4 is positive. So negative is decreasing, positive is increasing. And the question asks us where the function is increasing. So we say increasing here and here. So that's pretty much all we do. Next we find the local extrema, local minimum or local maximum. Pretty much the same thing. The only difference from what we have here is that this time we are asked to find the local extremum, meaning that we need to find the points, because the answer is going to be the point where the function has the maximum or minimum. So this we have to check the point. Right, so we still do the same thing. Take derivative. So we 4 x cubed minus 4x and equal to 0 does not exist. So that equal to 0. I can factor out for x. And we have x squared minus 1. Right. So for x equal to 0, or x squared minus 1 equal to 0. For x equal to 0, so x equal to 0, x minus 1 equal to 0, so move the 1 over, x squared equal to 1, take the square root on both sides, x equal to, make sure there's a plus or minus when we take the square root on both sides. And so that just x equal to plus or minus 1. So we have 0, 1, and -1. Right? Does not exist. This is a polynomial function. Polynomial function defined everywhere. So there's nowhere when the function is undefined. So that's why we have 0, -1, and 1. Remember, this time we're asking for the points, so we need to check the points. Critical points, maximum, minimum, that's where we have to check the point. With the original function, because the points, maximum, minimum, inflection point, critical points, all the points belongs to the original function. So always have to check with the original function. Right. So what is f of 0, negative 1, f of 0, and f of 1? Right. This calculator. This time I actually enter the original function. X to the 4th minus 2x squared minus 9. And then we go to the table. Because those values are integers. When x equal to negative 1, the function is equal to, sorry, put the calculator away. X equal to negative 1, the function equal to, sorry, right, negative 10. X equal to 0, y equal to negative 9, and when x equal to 1, it is equal to negative 10. Right. Next, we go to the sign chart. Right. On the sign chart, the number line on the top, negative infinity to infinity. The points we have 0, 1, and negative 1. I just need to put them in the right order. Negative 1, 0, and 1. This is where the derivative equal to 0. We have the derivative here for x cubed. So the sign chart is the derivative. Right. We're going to need the test point here. We'll choose negative 2, negative 0.5, 0.5, and then 2. Putting that in the derivative. Okay. Y equal to, enter the derivative for x cubed minus 2x minus 4x. Second table. That doesn't give us the fractional values. So in that case, its second trace is that values. Then we can enter the decimal values. Negative 2. Or any fraction, any rational numbers. Negative 2 give us negative 24, negative 0.5, positive 0.5, negative, and 2 is positive. Put the calculator away. Now, negative is decreasing, positive is increasing, so decreasing, increasing. Now, what we have is if the function going down and then up, that have to be a minimum, and if it go up and then down, that have to be a maximum, and so this is the minimum. So from there we will say this is a local minimum maximum equal to when x equal to 0. We know that when x equal to 0, the function equal to negative 9, so that's why we have negative 9. local mean at x equal to -1, also at x equal to 1. Now when x equal to -1, it is -10, and x equal to 1, it is also -10. So that's what we have. So not only we check to make sure that those points belongs to the domain of the function, we actually find the values, because right. Actually it looks like it's okay. So let's just continue. I hope it's okay. Won't be able to check until the end of the video though. Right. So this determine whether the function is concave up or concave down. So starting from here we have concave up, concave down. This is again concave up, inflection point. So concave up, concave down, inflection point. That's where we do the second derivative. But overall, still the same technique. Right. So first I will take the derivative. 3x squared minus 6x plus 2, and then take the second derivative. 6x minus 6. That's pretty much it. Right. Let's look at the problem. Determine whether the function is concave up or concave down. So this did not ask us for the points, asking for the interval. So we look for the interval. So that means we don't need to check the points. Right. We need the derivative equal to 0. Or derivative does not exist. Uh, 6x minus 6 equal to 0. So 6x equal to 6, or x equal to 1. Does not exist. Polynomial defined everywhere, so we have none. Don't need to check the points. Just go straight to the sign chart. This time we put the second derivative. Right? Only have one point. 1. That's where the second derivative equal to 0. So let's choose 0 and 2. Right. On this I just do it by hand. Put 0 in here, we have negative 6. And put 2 in here, 12 minus 6 is equal to positive 6. So it's positive. So this is negative. Remember, this is the second derivative. So for second derivative, if it is positive, it is concave up. If it's negative, second derivative, so the 2, it is concave down. So negative is concave up, negative, sorry, after all of that, negative is concave down, and positive is concave up. Yeah, the faces. So we write concave up is where x equal to, from an interval of negative infinity to 1, and concave up 1 to infinity, and concave down negative infinity to 1. Right, so that is just that. Right, next, for the largest interval where the function is concave up. So pretty much the same thing. I will take derivative and take derivative again. Usually I will use the quotient rule here, but look like derivative, we need the second derivative. So in that case, I will use a little bit differently. But before that, we asked to find an interval. So once again, it's actually open interval. So we don't need to check the point. If we're asked to find critical points, maximum, minimum, inflection points, that's where we check the point. If we're asked to find an interval, we don't need to. Alright, now take derivative. Instead of using quotient rule, I will write a function like this. X plus 2 at the bottom. Put the parentheses around it. Move the whole thing to the top. Change the power to negative. Alright, now we take the derivative. I'm going to use the chain rule. Ignore what is inside derivative of 3 times something to negative 1. Take the negative power down. Give us negative 3, the parentheses, and original power minus 1. Minus 1 minus 1 is minus 2. And then we'll take the derivative of inside. Right. So we have x plus 2. And x plus 2. Derivative of x plus 2 is just 1. So we have negative 3 x plus 2 to negative 2 times 1, which is just that. Right. Now we take the second derivative. Second derivative, similarly, let's put the parentheses there, and we don't really need to know what is inside derivative. It's going to be take the power down. Negative 3 times negative 2 is positive 6, and original power negative 2. Negative 2 minus 1 is negative 3, and then we have derivative inside. So we'll have derivative x plus 2 which is 1, so we don't have that. So that's all we have. Negative exponent move to the bottom. the power becomes positive. Right. Of course, you can use the quotient rule also. Derivative is just do that 2 times. Right. After that, derivative equal to 0. Derivative does not exist. Equal to 0 is where the top is 0. Does not exist where the bottom is 0. Right. So the top equal to 0, 6 equal to 0. Of course, that doesn't give us anything. The bottom equal to 0. X plus 2 cube equal to 0. Take the cube root on both sides. A power is equal to 0 if the base is 0. Minus 2 on both sides. So that's what we have. Right. Again, we don't need to check for the points. And then we do the sign chart. There's only one point that divides the number line is -2, and that is where the function is undefined. So here I just write does not exist instead of like 0 that I wrote earlier. Here I put the derivative, second derivative, 6 over x plus 2 cubed. Right, test point, -3, and that's 0. Calculator. I think there's a problem with the calculator that make the program frozen. Hope doesn't do that again. Right. Let's put that here. Right. Y equal to function 6, not the function, second derivative, 6 divided by x plus 2 cube. Right, just go to a table because those are nice and even number. -3, x equal to -3, it is equal to -6, and when x equal to 0, it's going to be positive. Negative is concave down, positive is concave up, and the question answers where the function is concave up, which is from -2 to infinity. It is always an open interval, so it's always parentheses for this type of problem. Right. Next, we're asked to find inflection points. Remember, inflection point, the point belongs to the graph of the original function. Therefore, every time we ask for the points, we need to check the points. And check with the original function. Right, I'll take derivative. Give us 6x squared plus 24x plus 18. And the inflection point, we need to do the second derivative. So that will be 12x plus 24, right? Do not the routine equal to 0 does not exist. Polynomial is defined everywhere, so there's nothing here. Second derivative equal to 0. So move the 24 divided by 12. So we have negative 2. Oh, that's all the point we have. Right. We asked to find the inflection point, so we do need to check it with the original function. X equal to 2, negative 2, sorry. Original function. So put negative 2 in it. I just use the calculator. Right. If we just evaluate at one point, I think the fastest way is just store the numbers into x. Negative 2 store into x. And then just enter the function. Because we only have one values to evaluate, so we don't have to do much. Let's give us negative 4. Right. We need to check the point. Right, next, the sign chart. Negative infinity to infinity at negative 2. This is where it is equal to 0. The second derivative equal to 0. I should put the second derivative here. Let's put x there. 12x plus 24. Right. If we put in 0, actually 0 would be here and negative 3 would be there. Right. I will just do that by hand. Negative 3 in here will be negative 36 plus 24, so that's negative 12. Put 0 in there, that's positive. Negative is concave down and positive is concave out. Let's go back to the question. The question asks us for the inflection point. Inflection point is where the concavity changes. So from concave down to concave up, or from concave up to concave down. Regardless, we have to have the change in concavity. We have the change here at x equal to negative 2. So in here, there is an inflection point where there is a change. So inflection point at x equal to negative 2. When x equal to negative 2, y equal to negative 4. So once again, not only we check to make sure it is in the domain, we check to get the values, because we do use the values later. Alright, so that's what we have. Next, we have the second derivative test. Since this problem is fairly similar, I only do 62. Right, so second derivative test, there's a few things. I'll write out what we need. Second derivative test, first of all, we have to have the derivative equal to 0. Let's test at the point. So we write c instead of x. It has to be equal to 0. If it is, then it is a critical point. And we can proceed to go to the second derivative. If the derivative does not exist or not equal to 0, we cannot go any further. Right. If it is positive, second derivative is positive, it is concave up, and that point would be a mean. If the second derivative is negative, it concaves down, and that would be a max. And that is the second derivative test. Right. So here, remember, I don't need to do the second derivative, first or second derivative, anything, because in this type of problem, the point will be given. So we just need to test them. Right. First, I'll take derivative. So that gives us 12 x cubed minus 12 x squared minus 24 x. Right. Let's evaluate at 0 the given point. Second derivative at 0, 12 times 0 cubed minus 12 times 0 squared minus 24 times 0, that is 0. So that's good. If it is equal to 0, then we say it is a critical point. If it is not equal to 0, then we stop there because it's not a critical point. Then we go to the second derivative. Only then, only when we know it is a critical point, we can go further. Second derivative equal to 36x squared minus 24x minus 24, and at x equal to 0, we take second derivative equal to 0. And of course that is equal to negative 24, because those being 0. Negative concave down, therefore it is the max. So we say local max equal to something. We don't need to do that at x equal to 0. So that's all we need to say. We don't have to find the maximum or minimum. We just say that it is the maximum at the point. We just need to know what happened at the point, maximum or minimum. We don't need to test them. I don't need to find the actual values. Right. Next we'll have a work problem here. Right. So a shipping company, we have the length plus the girth does not exceed 120 inches. So let's say this box would have the square end. So we just say if we have x here, x there, x and x, because it has the square end, so this should be a square, or that could be a square. Let the length be y. So we start with the volume. They say what will give us the largest possible volume. Volume of a rectangular box is length times width times height. Length times width times height. So pretty much x times y is x squared y. So that's what we have. Next, we have the length plus the parameter here cannot be more than 120. So if it is cannot be more than 120, it will be maximum at 120, even though it say 120. Of course, if we want to use the maximum, we have to use the full numbers. I mean, the capacity, use all the capacity that we have. So it have to be equal to 120. So we write the length, which is y, plus the girth, which is 4x, has to be 120. And we solve for x or solve for y. If we solve for y, it is equal to 120 minus 4x. And we can just substitute this in for y. And so we have the volume equal to x squared 120 minus 4x. So 120 x squared minus 4x cubed. That's what we have. Right. Let's go back to the first problem. Actually, this time we asked to find the absolute maximum and absolute minimum. So to do that, we need to have an interval, so we know if the point's actually in there or not. Right. So to do that, let's look at this condition. X cannot be negative. Obviously, the measurement cannot be negative. Same thing for y, cannot be negative. So we have x greater than or equal to 0 and y greater than or equal to 0. But remember, y equal to 120 minus 4x. So that have to be greater than or equal to 0. Move the 4x over 120. Add 4x on both sides. Or just let minus 120 on both sides. It's better that way. So we have negative 4x greater than or equal to negative 120. And divide by negative 4 on both sides. Since we divide by a negative number, the inequality must be reversed. So if x less than or equal to 30, now we have x greater than or equal to 0 and less than or equal to 30. So that is the boundary for our problem. For x greater than 0, greater than or equal to 0, and less than or equal to 30. Right. So this is the problem that we have. Right. And then after that, we take the derivative equal to 0, does not exist, and then we test at the boundaries. So, derivative of this is 240x minus 12x squared. Right. Derivative equal to 0. Derivative does not exist. Right, equal to 0. 240 minus 12x squared. 240x minus 12x squared equal to 0. I will factor out 12x. Then I should have 20 minus x equal to 0. So we have 12x equal to 0, or 20 equal to x. Yeah, just move the x over, and that's it. So x equal to 0 or x equal to 20. Does not exist, there will be none. Right, there are a bunch of options that we can do here. We can do like what we did here. I'm sorry, here. Put everything in the table. The biggest the max, the smallest is the mean. That's usually the easiest one. But also on this one, remember, we do have to check 0 to 30. Between 0 and 30, there's only one point, 30, because 0 is considered to be boundary point, so it doesn't count. Between those boundary points, there's only one. So if it is exactly one critical point in the middle, if it go like this, that will be max. If it go like this, that will be a mean. So when we have one critical point, which is 20, belongs to that, then if it is the local max, then it is absolute max. If it is a local mean, it's absolute mean. So let me write out the important things here. So since there is one critical point, you only have 20. In the interval, in the domain. If that is the case, then local extremum is also absolute extremum. Right. Remember, we asked for the largest possible volume, so we asked for the absolute maximum. Right. But because this is one critical point, we don't need absolute maximum. Local maximum will also be absolute maximum. So in that case, just need to show that at this point it is a local maximum. So we can use a sign chart, but what we did earlier, remember the second derivative test. If we take the second derivative, we have 240 minus 24x. Then we evaluate at 20. We put 20 in it, and that negative 480, and this is give us negative 240, which is negative. So what we have is local, which is also absolute, because of this theorem, one critical point. Local and absolute max at x equal to 20. They did not ask us what is the maximum volume. They asked us for the dimension. So all we need to do is just give the dimension. We know x is 20 and y is equal to 120 minus 4x. 4 times 20 is 80. 120 minus that is 40. So the dimension of the box is 20 by 20 by 40. The square end and the length is 40. Right. I will not do the next one. I just give you a little hint to start with. So I have a piece of molding 188 centimeter long. We're going to cut and form a rectangle. So let's cut in half, and with that we have a little x, y, x, and y. We'll cut of this length, put them together, we have a little box like that. We ask to find the largest area, meaning that we have the function equal to xy, and we need this to be maximum. Right. And then all of this, of course, 2x, actually x plus y plus x plus y, the total length has to be 188. So 2x plus 2y is 188. Shown for y, substitute in here and then find it. Right, I'm not going to do that. I'll let you do it. Right. Next we see if we do something else. So this one asks use the differentials to approximate the quantities. So this is a linear approximation. So let me write out a linear approximation. Our formula for that is exactly the equation of the tangent line, because we do use the tangent line to approximate the values of the curve. Will be the derivative at a point times x minus a plus f of a. So what's a? What's x? So x is the number that is close to the prime. I mean, x is the actual numbers. And the actual values of x. And a is the values that we choose. The values that we choose to be close to it. So will be the chosen values. Of course, if we choose the numbers, we choose something that will be very easy to calculate. Chosen values is close to a, close to x, and it's easy to evaluate. That one obvious. Right. So for this kind of problem, the first thing we do is look at the problem. Whatever numbers we have, that will be x. So 145 is x. So we're going to let x be 145. If that is the case, we will have the function, instead of 145, it is square root of x. Right? And then we choose the values. We choose something that is close to it, but the values is very nice to calculate. So I will choose something that when the square root come out nice and even. So something close to 145 as well. How about square root of 144? Because square root of 144 is 12. So just have to choose something close to it and very easy to evaluate. So that's easy. Right. Next, in this case, we need to find the derivative and the values of the function at that point. Right. If we want the function to be easier to take derivative, we can also use 1/2. Right. First, the function is 1/2 x to the 1/2. We'll evaluate at x equal to 144, the nice numbers here. So at x equal to 144, f of 144, we can use either one of them. 144 to the 1/2, square root of 144 is 12. Then we'll take derivative. Will be 1/2 x to negative 1/2. We will evaluate at the nice even number here. Let's use a calculator. Negative 1/2. Sorry. Negative 1/2 times 144 to the negative 1/2. Equal to Alright, usually we'll prefer to have a fraction, but on this problem, since it is a problem of approximation, we can just take the decimal, just take a bunch of decimal places. But anyway, I'll use fraction. -1 over 24. Right. Then go back to the linear approximation, the formula. The values of the function is approximately equal to the derivative at the ninth point plus the function at the ninth point. Ninth is something that is easy to evaluate. The derivative we calculate is -124 x 145 minus a 144 plus the values of the function 12. So we just do that because 144 minus 1 is 1 times that, so -1 over 24 plus 12 -1 over 24 plus 12. They want to 4 decimal places, so we have I apologize, there's no negative here. Yeah, so derivative, there's no negative. This is 1/2 x to -1/2. Sorry. Right. Again, 1 over 24 instead, plus 12 is 12.04, 4 decimal places, 12.0417. Right. So that is an approximation. If we want the actual values, what is the square root of 145? As you see, the approximation and the actual values are very close. So this is a very good approximation. Usually, if the point we choose is very close to it, the approximation would be good. Right, next one. First, whatever the number is given, that will be x. So because of that, the function is sine of x. Then we choose something nice and even, but have to be close to x. Obviously, the one that is nice and even and close to it, I would choose x to be 0, because sine of 0 is 0. That's easy to evaluate. That's the nice values there. Right, so we'll evaluate the function. At x equal to 0, sine of 0 is 0. Derivative is cosine x. Evaluate x equal to 0. Derivative at 0, cosine of 0 is 1. Then the formula for linear approximation. The values of the function approximately equal to the values of the tangent line at 0. We could put 0 there if we want to, but let's just use the formula. Derivative is 1. The values of the function are 0. X minus a, x is that minus a0. So we have x, that number, minus 0. Right. So negative, again, let me just copy that. That just gives us negative 0.01. They want 4 decimal places, but we only have 2. We can write 0, 0. Yeah. There, 4 decimal places. If we actually were trying to find the values of sine of negative 0.01, make sure it is in the radian mode, because there's no degrees here. Sine of 0.01, actually it is negative 0.01, and that's what we have. Of course, that value is extremely close to the approximation values that we have, the exact values that we need to have, which is good. So that's all. Next, just need to do that. So it's very simple, and notation should be pretty obvious too. So we just simply take derivative. Except this one is the chain rule. Sine of something, derivative of sine is cosine, but then we have to take derivative of that something. Doesn't matter what is inside the parentheses, that's what we do. We put 3x squared here and 3x squared here. Derivative of cosine, actually there's nothing there, nothing we can do here. Derivative of 3x squared is 6x. I prefer to put the 6x in front, so we don't have to put the parentheses here. Right. Then let's just rewrite the notation. Instead of write f prime of x, why don't we write dy over dx? Let this function be y, so we can write like that. So dy over dx is equal to 6x cosine of 3x squared. Just move the dx over. That's what we have. The next one kind of similar as well. Find the approximation values, radius increase from that to that. Right. Let's say what we have. This is the volume of the sphere. Volume of the sphere, V equal to 4/3 pi r cubed. And we take derivative. So we have dv over dr equal to, take that to 3, so it will be 4 pi r squared. R squared. Right. And just like what we did, swing the dr over. Now, the only thing different here is the approximate the change in the volume. So we want the actual change. So instead of write dv dr for a very small number, we write delta v. So it's no longer equal to. And we'll write dr. dr here is the change in the radius. It goes from negative 5.2 to 5.3. So delta r. So always final minus initial, where we find the change. So 5.3 minus 5.2 equals 0.1. So delta R is 0.1. And then R is 5.2. Put this in this equation. We should have 4 pi 5.2 square 0.1. 4 pi 5.2 square times 0.1. We have about that 33. $33.97. This is the change in volumes. So we just write the unit for the volume, centimeter cube or cc. I'm going to write the timestamp. Right, next, find the values of C that satisfy the equation of the mean value theorem. So the mean value theorem say that the average rate of change throughout the interval is equal to right. So this is the average rate of change or the slope of the secant line. There will be a point in the middle, so the tangent line will have the same slope as that secant line. So I just draw the pictures here. So let's say there's 1 and 2. There's some values. It might go like this, possibly. And then we will draw the secant line go through the end point. And the mean value theorem says there will be a point in between 1 and 2. The tangent line will be parallel to the secant line, meaning that they have the same slope. So pretty much we're going to do both. First we'll find the slope of the secant line. So that is the slope of the secant line, or the average values of the function. So we take the values at 2 minus values at 1 over 2 minus 1. So we do that. Right. I just want to do this so we can review. X squared plus 3x plus 4. What we have is the function at 2 minus the function at 1. So I hit second mode to quick. Variables, y variables, y1. We evaluate that at 2 minus variables function y1, evaluate that at 1. That gives us 6 over 2 minus 1, so that's just 6. So that is the slope of the secant line. The slope of tangent line just derivative, which give us 2x. 2x plus 3. We don't know what point in the middle yet, but we do know there will be a point in between 1 and 2 where these two are equal. So we have 2x plus 3 equal to 6. Move the 3 over, 2x equal to 3. So x equal to 3 halves. So that's what we do. Next we have L'Hopital rule. Right. So L'Hopital rule, it only applies to the indeterminate form 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity. Those are the indeterminate form. So if we have any of this, we can use the L'Hopital rule. Right. So the first thing we do is just put in the numbers to see if we have the indeterminate form. I put in -5, -5 squared, 25 minus 25, 0 over 0. So that's good. This is one of the indeterminate form. So we can use the L'Hopital rule. And the L'Hopital rule says we'll take the derivative of the top and derivative of the bottom. This is definitely not the quotient rule. Derivative of the top 2x, derivative of the bottom 1. Then we're just going to put, so that just, let me just write out. Then we're going to just, the first thing in limit is just put the numbers in and see if we have anything nice and even, and we do. So that's pretty much the limit. So that's it. Next we do the same thing. We'll put 0 in for x. Cosine of 0 is 1 minus 1. So in that we have 0 over 0, which is one of those indeterminate forms. So we can use the L'Hopital rule. Which means we take the derivative of the top, derivative of the bottom. Derivative of the bottom, that's easier, 2x. Derivative of the top, so that is chain rule. Cosine of something is negative sine of something, and then derivative of that. Derivative of 1 is 0, so we're not going to need that. So that's pretty much it. Derivative of 7x is 7, so negative sine of 7x times 7 over 2x. Right. I don't have the space here, so let's just write limit x go to 0 of negative 7 sine of 7x over 2x. Now if we put in 0 again, so remember I don't write equal sign here yet. Put in 0, we have negative 7 sine of 0 over 2 times 0. That is 0 over 0, which is also indeterminate. So we keep using the L'Hopital rule. As long as we still have indeterminate form, we still use the L'Hopital rule. If we don't have indeterminate form, never use the L'Hopital rule for something that is not indeterminate. Right, meaning derivative of the top, derivative of the bottom, derivative of the bottom is just 2. I put the parentheses around this. Derivative of sine is cosine. So I have negative 7 cosine of something, and then derivative of that thing. Derivative of 7x is 7. 7 times negative 7 is negative 49. Cosine of 7x over 2. And then we're going to put 0 in it. Negative 49 times cosine of 7 times 0 over 2. And cosine of 0 is 1. So we have negative 49 over 2. And that's what we have. Because that's a nice number, not indeterminate. So we just make it equal to. I forgot to write the timestamp for that one. But I do have one. Right. This one, usually we use the Harper rule. Actually, we can use the Harper rule, but I will just skip it when we don't have to. We don't have to do that. I remember back in the first section, the first chapter, that is where we find the limit. As x goes to infinity, polynomial only depends on the highest power term. The highest power term on the top, highest power term at the bottom. So we just take the ratio of those terms. Cancel out the x. 5 over 7x. If we put infinity to it, the top is a finite number, the bottom is infinity, so the limit goes to 0. Much better than to use the Harper rule. That's what we do, really. Right. Last problem on this review. Right. Remember, the Harper rule only applies if we have a fraction. So we're going to make a fraction out of this. The sign, we won't be able to do anything there. But the x, we try to the first power. Let's move to the bottom, become negative. Likewise, we can write 4x to negative 1 as well. Right. Now a bit more complicated when we evaluate. So first we put infinity in it. Right. By the way, infinity to the negative 1 power is like 1 over infinity, which is 0. So when x go to negative, x go to infinity, x to negative 1 goes to 0. So by that I mean, as x go to infinity, x to negative 1 goes to 0. So this pretty much we have sine of 0 over 0, which is 0 over 0 indeterminate. Right, which means we can use the Harper rule. Right, this is a chain rule. So the derivative of sine is cosine, and then derivative in sine. Derivative of the bottom, take down the negative 1, we have negative x to the negative 2. Right. Limit x goes to infinity. We have cosine of 4x to negative 1. Cannot do anything with that. 4x to negative 1 derivative is negative 4x to negative 2. take out the -1, original power -1. Of that over x to -2. We can cancel the x to -2. So this equal to limit as x go to infinity sorry, I forgot this negative sign, right? And that negative sign also cancel out. And there's a 4. And there's nothing at the bottom, so we don't need the denominator. So we just have cosine of 4x to -1 times 4. Notice, as x go to infinity, x to -1 go to 0. So here we just have cosine of 4 times 0 times 4. Cosine of 0 is 1 times 4 is 4. So that's a nice number. So we make the limit equal to it. Right. With that, we complete all the questions in this review. We continue on the next one after this. But that's all we have for now. I hope you find this helpful. Thank you for watching.